We have been discussing diffraction, and we saw that if we have a periodic arrangement of sources, for example, we considered the diffraction grating where there was a periodic arrangement of slits, and we saw that when we have a periodic arrangement of sources, we get a diffraction pattern where there is a consecutive set of bright and dark fringes observed. And the diffraction grating is essentially a one dimensional periodic arrangement of sources. Each slit acts like a source, and there it is a one dimensional arrangement. If you make the slit width and the length of the slit comparable, you then have a two dimensional situation. You could have a pattern of squares, for example, which could act like a two dimensional periodic arrangement of sources, and you would also get a diffraction pattern in such a situation. Today we are going to discuss a very interesting situation where we have a three dimensional arrangement of three-dimensional periodic arrangement of sources. We all know that the distribution of atoms and molecules inside crystalline solids, it has a periodic arrangement. So, there are certain solids which are crystalline, for example, salt NaCl has a crystalline structure or diamond, and the distribution of the atoms or the sodium chloride molecules inside these solids, it is known that it has a periodic structure. And this periodic structure, this periodic distribution of atoms or this periodic distribution of molecules could act like some sort of a diffraction grating. So, this is the situation that we are going to discuss in today's lecture. So, this shows you a schematic diagram of the distribution of atoms, or it could be molecules, inside a crystalline solid. And we are going to discuss a situation where this is going to act like a diffraction grating. So, each of these atoms, each atom is going to act like a source of radiation, coherent source. So, the radiation from all of these atoms is going to be coherent, and we are going to consider a situation where there is diffraction. So, you superpose the coherent emission from all of these sources, and we can get a diffraction pattern. Now, we know that the interatomic spacing is of the order of angstroms. So, the interatomic spacing, which I show by A over here, A is we are going to use A to denote the interatomic spacing or the unit cell, the cell spacing, and this is of the order of 1 angstrom. This is known that the distance, typical distance between atoms inside crystalline solids is of the order of 1 angstroms. And we saw that the diffraction, when we considered grating, for example, the diffraction, the condition for the maxima is d sin theta is equal to m lambda. You get the maximas at different angles theta, provided this formula is satisfied. So, the maximas, the angular spacing between the maximas is of the order of lambda by d, and where d is the spacing between the sources, right. So, in this case we are going to consider a situation where these interatomic spacing is d. So, it is of the order of 1 angstrom. So, we have to, what this tells us is that we have to consider some kind of a radiation, some kind of a wave where the wavelength is of the order of 1 angstrom. So, we have to consider a situation where the wavelength of the radiation is of the order of 1 angstrom. So, the wavelength which we are going to use is of the order of 1 angstrom. And we have discussed the electromagnetic spectrum, and we saw that 1 angstrom is X-ray. So, the wavelength range around 1 angstrom corresponds to X-rays. So, we are going to consider a situation where there is X-ray incident on a crystalline solid, and this is what is shown over here. You have X-ray which has a wavelength of the order of 1 angstrom, which is incident on a crystalline solid. Now, what is going to happen when you have X-ray radiation? X-ray, remember, is an electromagnetic wave which is incident on a solid, on some crystalline solid. Now, electromagnetic radiation, we have discussed several number of times that electromagnetic radiation is an oscillating electric field. So, the way you should think of this incident electromagnetic radiation is actually in terms of a wave, and this wave has an oscillating electric field. So, this is the electric field, let us say hypothetically, and there is going to be an incident wave of electric field which is oscillating. There will also be a magnetic field. Now, you have these so you have this electromagnetic wave which is incident on this solid, and this picture shows you the atoms which are arranged periodically inside the solid. Now, the atoms we know have a nuclei and they also have electrons. Now, when these atoms, when an individual atom is under the influence of the external oscillating electric field, so we have an atom under the influence of an external oscillating electric field. The oscillating electric field is the X-ray, the electromagnetic wave, and the atom is under the influence of this external oscillating electric field. Both the nucleus and the electrons are going to experience this oscillating electric field. Now, the acceleration of the nucleus is going to be much smaller, because the acceleration of any particle under the influence of an electric field is E, the electric field, into the charge divided by the mass. The mass is, this is the acceleration on the particle, and the nucleus is much heavier than the electrons. So, the acceleration of the electrons is going to be much larger than the acceleration of the nucleus. So, the electrons in this atom are also going to accelerate in response to this external electric field. They are going to experience an external force. Now, we can think of the electrons as being bound to the nucleus. The electrons are actually bound to the nucleus, and we can think of this, if the external disturbance is small, I have told you that you can think of the response as that of a simple harmonic oscillator. So, we can think of the electron as being bound to the nucleus by some kind of a simple harmonic oscillator potential, by a spring, and there is an external force which has a frequency. The frequency is the frequency of the X-ray radiation. So, we have a simple harmonic oscillator, the electron bound to the nucleus, which is under the influence of an external force. The external force is because of the X-ray which is incident, you have this oscillating electric field. And we saw that the electron, if you look at the large time behavior, the oscillator is going to oscillate at the frequency of the external force. It is going to oscillate at the frequency of the external force. So, the electron inside the atom is going to oscillate at the same frequency as the X-ray. And we also saw that when an electron oscillates, it emits electromagnetic radiation. An oscillating electron emits electromagnetic radiation, and this radiation again is at the same frequency at which the electron is oscillating. So, let me recapitulate what I have told you. When I have X-ray of some frequency incident on the atom, it is going to set the electrons into oscillation with the same frequency, and the electrons are going to emit radiation at the same frequency. So, if I have electromagnetic radiation of frequency nu incident on this solid, on this crystal, the electrons inside this are going to radiate at the frequency nu. The electrons inside here are going to radiate at the frequency nu, and the oscillating electron are going to the electrons inside are going to oscillate at the same frequency as the X-ray, and the oscillating electron, it's a dipole oscillation, is going to emit radiation in various directions. So, this is going to radiate emission at the same frequency nu in various directions, and we have discussed the direction dependence of the dipole radiation. So, each atom, the bottom line is that each atom over here is going to act like a source of radiation at the frequency nu, and all of these sources are going to be coherent. So, we are going to have coherent radiation coming out from each of these atoms, and this radiation is going to be at the same frequency as the incident X-ray. The incident X-ray is there only in one direction. Each of these atoms is going to scatter it out. This is called Thompson scattering. Thompson scattering. Thompson. So, you are going to have this radiation coming out, and to determine the intensity pattern in different directions, you have to add up the radiation from each of these, this periodic arrangement of sources. And we have seen that if you have a periodic arrangement of sources which are radiating coherent, all of them are radiating the coherent radiation. So, the radiation from here, here and here, if they are coherent, then you are going to get a diffraction pattern. So, what we have over here is X-ray, a diffraction pattern that is going to be produced by the radiation from this periodic arrangement of sources. Each atom is going to scatter out radiation in all directions, and if you look at the intensity in a particular direction, you are going to get the sum of the radiation from all these atoms with different phases. This is quite a complicated situation, because now you have a three-dimensional situation. When you dealt with slits in a diffraction grating, you had just a one-dimensional distribution. Here you have a three-dimensional distribution of sources, so it gets a little complicated. But there is a simpler way of thinking about it, which was pointed out by Bragg, and what the way you think about it is that you can think of this scattering from these atoms in terms of planes. So, this is the crystal, the same crystal lattice, the atomic spacing is A, the interatomic spacing is A, and each of these atoms sends out radiation, and we are interested in the resulting diffraction pattern. So, what Bragg said was that you can think of this as in terms of planes. So, if this is the crystal, I can draw planes. So, this is one plane. I can draw different sets of planes. This is one set of planes. So, here I have one particular set of planes, and these are the planes drawn in red. And this scattering I can think of as follows. This is the incident radiation. It gets reflected over here from each of these planes, and if I am interested in the So, if I am interested, so if I consider a situation where the light is incident at a grazing angle theta. So, the light is at the X-ray is at a grazing angle theta, and we want to see what is going to be the incident, the intensity of the radiation that is scattered out, rather reflected out from these planes. So, it is going to be reflected out at the same angle theta, and the wave that is reflected from the first plane is going to be at a phase difference with respect to the wave reflected from the second wave, which again is going to be at a phase difference with respect to the radiation reflected from the third plane, and the phase difference corresponds to this path difference, because this has to travel a larger distance. So, there is an extra path, and this is the extra path. So, you will have a set of waves. If I look at the radiation in this direction, in the reflected direction, I will have a set of waves, but these waves are going to have a phase difference. So, there is going to be a phase difference between this and this, this and this, and this phase difference corresponds to this path difference. And if you work out the condition that they should all be in the same phase, you will get the condition that 2d sin theta is equal to m lambda. 2d sin theta by lambda is the path difference between two consecutive the waves reflected from two consecutive planes, and if this is an integer multiple of the if this is an integer if the path difference is an integer, the path difference is 2d sin theta, if the path difference is an integer multiple of the wavelength, we know that this is they are going to be in phase, and that is the condition for a maxima. So what Bragg proposed, this is called Bragg's law, is that we can think of this complicated situation in terms of reflection from a set of planes drawn through the crystal, and this is a particular set of planes. You can have many set of planes, this is one possible set of planes. You could also have planes like this, and you have to consider all such possibilities. This is one possibility which I have shown here. So we are considering only one possibility, and if you will get a maxima if this condition 2d sin theta is equal to m lambda. Let me show you another possible set of planes. So this shows you another possible set of planes which can be drawn through that crystal, and you have to consider, when you have X-ray incident on this lattice and you want to find out where the maximas will occur, you have to consider reflection from all such planes, and the maximum will be, you will get a maxima if the condition 2d sin theta is equal to m lambda, if this condition is satisfied for any of these planes. Now there are three indices called the Miller indices, which are used to quantify, to label these planes. So there are three indices called the Miller indices which are used to label these planes, and the set of planes drawn over here correspond to Miller indices H, K, L. So the Miller indices are called the symbol used for the three Miller indices are H, K and L, and these particular planes correspond to H, K, L values 1, 0, 0. So let me spend a few minutes and explain to you what we mean very briefly by these Miller indices. So let me draw a picture in 2 dimensions again. So this is my crystal. This should be here, here like this. Let me draw another set and then we can start the discussion. So this is my crystal, let us say. Let me call this the x axis and this the y axis, and I also have the z axis. Now I can draw a plane through this crystal, which set of planes which go like this, and these planes have intercept unity in terms of the spacing, interatomic spacing. They have a set, an intercept unity along the x axis. So H, K and L refer to the intercepts of these planes with the x, y and z axis. So the intercept, the distance between the intersections of these planes and the x axis here is 1. The planes never intersect the y axis or the z axis. So H, K, L equal to 1, 0, 0 label these set of planes. I could also consider a situation, the same, let me draw the same lattice, the same crystal, again I have the x axis over here and the y axis over here, and I could have planes which are vertical now. Now these planes, they never intersect the x axis, they never intersect the z axis, but they intersect the y axis, and the separation between these intersections is 1, 1. So H, K, L have values 0, 1, 0 for these planes. Again, I could have another set of planes which are like this. And these, the green ones, have H, K, L values 1, 1 and 0, because they intersect both the x axis and the y axis, and this spacing is 1, this spacing is also 1. So, corresponding to different set of integers h, k, l and h, k and l, I will get different planes which can be drawn through this crystal, and this crystal that we are considering is a cubic lattice. I have shown you only a section through the cubic lattice, but along this is the x axis, this is the y axis, along the z axis also the arrangement is exactly the same. So, we are considering a cubic lattice, and in this cubic lattice I can have different kinds, many different planes, and the interplanar distance d is what is referred to as d. Okay, the interplanar distance is what is referred to as d. So, let me show you another example. Through the same crystal, now I have drawn these planes at 45 degrees. These planes also go through atoms, and they are, so the arrangement of atoms looks the same on these planes, and these planes have indices, Miller indices 1, 1, 0, because that is where they intersect the x and y axis. They don't intersect the z axis at all. That is why they have Miller indices 1, 1, 0. For different values of the Miller indices, I will get different planes through this solid, and there are different possible integers which are allowed. They will all, different integers will give you different planes. Now, the next question is, what is the interplanar spacing corresponding to these planes? So, for these planes, the interplanar spacing is exactly the same as the interatomic spacing, it is a. For these spacings, these planes, you can see that the interplanar spacing is, if you apply Pythagoras theorem, the interplanar spacing, you can calculate it for these planes, and it is going to be, you can, so this is the interplanar spacing, and you can see that it is 1 by square root of 2 of times the interatomic spacing. So, in general, the interplanar spacing d, which is dependent on h, k, l, the three indices which label the planes, is going to be the interatomic spacing a divided by the square root of h square plus k square plus l square. So, we are going to have maxima for corresponding to theta. Theta, remember, is the grazing angle and not the incident angle which we have been using earlier in diffraction. It is the grazing angle, it is the angle with reference to the plane and not with reference to the normal. So, whenever the condition 2d sin theta is equal to m lambda, whenever this condition is satisfied, you are going to get a maxima in the intensity pattern. So, I have explained to you over here and told you the, I have told you the basic idea and also the condition under which you will get a maxima in the diffraction pattern when you use X-ray, when X-ray is incident on a crystal. Now, let me next discuss a device called the X-ray diffractometer. X-ray diffraction, incidentally, is a very useful technique to determine the structure of materials. So, if I give you a crystal and I do not know its interatomic spacing, I do not know how the atoms are arranged, I can use the diffraction pattern to determine the interatomic spacing and the structure, the arrangement of the atoms inside this crystal. So, there is a device called an X-ray diffractometer, and let me briefly explain this X-ray diffractometer. So, we have X-ray incident. So, there is X-ray which is incident on the sample. So, this is my sample. So, there is X-ray incident on the sample, and the sample is a single crystal, or it could be, the sample is a single crystal over here, or it could be many single crystals. Whichever be the case, there is going to be X-ray scattered in all directions. The intensity of the scattered X-ray is going to vary with the direction, and what happens in this X-ray diffractometer is there is a X-ray camera or X-ray a device which can measure the intensity of the scattered X-ray, and this device is moved to different angles and it measures the intensity of the scattered X-ray as a function of this angle, as a function of this angle over here. Now, let us just see what is the relation between the angle over there and this theta, the angle, the grazing angle made with the planes inside the crystal. So, this sample over here is a crystal. It has, let us take a crystal inside this sample, and inside the crystal we can draw planes. So, let us consider a set of planes. The planes could correspond to any of these Miller indices, but so there could be some planes inside that crystal. So, let us say that these are the planes. So, the X-ray is incident like this, and these are the planes inside the crystal which is a part of the sample. Now, if the planes are like this, if the planes are oriented like this, then this grazing angle is theta, which is also the angle over here, and the angle, the reflected angle over here is also theta, the reflected grazing angle. So, you can identify this angle, that the angle of the scattered X-ray with reference to the incident X-ray as being twice theta, where theta is the grazing angle with respect to the plane. So, if you measure the intensity in this direction, then it would have made this, the X-ray scattered in this direction has been scattered by planes which make a grazing angle theta. If this angle is 2 theta, then this planes, the planes which have scattered the X-ray in this direction are at the grazing angle of 2 theta. Okay. So, you can measure the intensity of the scattered light as a function of this angle, which you can interpret as being twice the grazing angle with respect to the planes which have scattered the X-ray in this direction. And what you get is the intensity pattern as a function of this 2 theta from the X-ray diffractometer. Let me consider an example over here. So, I am going to show you a particular example, and the example which we are going to consider, we have lanthanum, strontium, manganese oxide. So, we have a crystal which has a crystal structure which is known. So, the crystal structure of this solid is shown over here. In this solid, the solid is essentially lanthanum manganese oxide, but over here strontium has replaced some of the lanthanum atoms, and the lanthanum atoms which have, or the strontium atoms, they are shown in red. So, the red ones are the lanthanum atoms. Some of the lanthanum have been replaced by strontium. The green over here is the manganese, and the yellow atoms are the oxygen. So, this lanthanum strontium manganese oxide is one cell of the crystal. So, we are considering a crystal, like this, and a unit cell of that crystal, a unit cell. So, each of these spheres you may think of as a unit cell of that crystal is one such lanthanum strontium manganese oxide, So you have a periodic arrangement of such lanthanum manganese strontium lanthanum strontium manganese oxide, and so you have now a sample made up of that lanthanum strontium manganese oxide on which you have X-ray. And what you have done is, what the diffractometer does is, it measures the intensity of the scattered X-ray as a function of this angle, which is called 2 theta. And this shows you the intensity which is measured at different angles 2 theta. So the x axis has 2 theta, the y axis has the intensity, and notice that as you vary the angle, as you vary this angle 2 theta, you find that there are maximas in certain directions. So in certain directions the X-ray, scattered X-ray has a very high intensity, and these you can interpret as being the maximas of the diffraction pattern. So these are directions where this formula 2d sin theta is equal to m lambda is satisfied. So in this picture, these lines are the X-ray maximas, and what you can get from the X-ray diffractometer is the intensity, the angle where you have the different maximas. And this table shows you the angles where you have the different maximas. The wavelength of this radiation of the X-ray, incident X-ray, is 1.542 angstrom. And what has been done here is, we have taken this graph and measured the angle corresponding to these maximas. So the smallest angle where you have a maxima is corresponds to 2 theta, being 23.10 degrees. So this is at 23.10 degrees, and remember that this angle is actually 2 theta is the total angle between the incident direction and the scattered direction. So the smallest angle at which you have a maxima is 23.10 degrees, then you have a maxima at 32.72 degrees, which is this one, and then you have a maxima at 40.33 degrees, which is the one over here, and I have not shown you the values corresponding to these other maximas. Now the question is that we have to interpret these different maximas. So there are two things which could change. The first thing that could change is the value, the order of the maxima m, or this value of d. D is the spacing between the planes, and if I change the planes, there are many possible planes through the crystal. If I change the Miller indices, the value of d is going to change. Also, the order of the maxima could be different. You could have a first order maxima, second order maxima, third order maxima, etc. The 0th order maxima corresponds to sin theta equal to 0, theta equal to 0, which is the direction of the incident radiation itself, and that we are not interested in. So now people who do X-ray, they know that the intensity of the higher order maximas, m equal to 2, 3, 4, 5, etc., is much smaller than the intensity of the first order maxima. So m equal to 1, it is known that m equal to 1 has a much higher intensity compared to m equal to 2 and higher orders. So in our discussion, so typically when you interpret these X-ray maximas, the diffraction pattern, the X-ray diffraction pattern, you can interpret the bright lines as being m equal to 1, which is what we are going to do over here. So experience with X-ray basically tells us that you are going to see mainly the first order maxima, and you can interpret all of these lines as being due to the first order maxima. So we are going to take m equal to 1. So, we are going to restrict our attention to m equal to 1. So, the condition for maxima is 2d sin theta is equal to lambda. Now, there are many possible planes which can be drawn through the crystal. I have shown you one example, but you could have many other planes, and these planes d is going to be the interatomic spacing divided by the square root of h square plus k square plus L square. And we can write this as sin theta is equal to lambda by 2d. Now, let us go back to the intensity pattern. This is the intensity pattern, and ask the question that what does this smallest angle of theta, what does this correspond to? So, when theta is smallest, we can say that d, see this only thing now that you can vary is d, the plane, the interplanar spacing, theta and d. So, any change in theta you can interpret as being a change in d. So, this maxima corresponds to a particular value of d, this corresponds to a different value of d, this corresponds to another value of d, and d will change for the same crystal. For a crystal, A is fixed, that is the interatomic spacing, the interlattice, that is a lattice constant or the periodicity of the crystal. So, d can change because of the change in the Miller indices. So, you can look at different possible planes, you have this possibility or you have this possibility, and this has a smaller value of d compared to this. So, the largest value which d can have is d equal to a, and d will be necessarily smaller than or equal to a. Now, if you reduce the value of d, this is going to get larger, and sin theta has to be equal to this. So, theta also will have to be larger. So, smaller value of d means larger angle theta. So, we can interpret, what this tells us is that we can interpret the smallest angle theta, the smallest possible angle theta, as arising due to the largest possible value of d, and the largest value of d is when h equal to 1, k equal to 0, L equal to 0, or you could have also had h equal to 0, k equal to 1, L equal to 0, or h equal to 0, k equal to 0, L equal to 1. All three of these will give you d equal to a. So, d equal to a is the largest possible, or rather d equal to a is the largest possible value of d, and this is going to give you the smallest angle theta. So, this is going to give you the maxima at the smallest angle theta. So, we can interpret this line as arising from d equal to a, and the angle corresponding to that line is 23.10 degrees. So, 2 theta (23.10 degrees), which means that theta, so we have to determine theta, and theta is 23.1 divided by 2, which gives us 11.55. So, this is 11.55 degrees, and d is equal to, let us determine d from here, d is equal to lambda by 2 sin theta. So, it is lambda by 2 sin theta, and this gives us 1.542 divided by 2 into Armstrong 2 into sine of 11.55. Let me calculate that. So, I have to take the sine of this, which is 0.20. So, this into 0.2. So, let me now do the calculation. Into 2 equal to inverse of that into 1.542, and it gives me 3.85. So, it tells me that the value of D for this is 3.85 Armstrong, and the smallest angle theta we can interpret as being H equal to 1 and the other two, which tells us that D is equal to A, which is 3.85 Armstrong. So, we can use the smallest angle theta to determine the interatomic spacing, and it comes out to be 3.85. Now, let us check if this gives us consistent results for the next one, the next intensity maxima. The next intensity maxima is found at an angle 2 theta equal to 32.72. So, let us check this. So, the next intensity maxima occurs at 2 theta is equal to 32.72, or theta is approximately equal to 16. Theta is equal to 16.36, and D is equal to lambda by 2 times sine theta, which is the wavelength of the X-ray is the same, 1.542 Armstrong divided by 2 times the sine of 16.36. So, let me do that. 16.36, the sine of that, into 2, okay, 16.36 so this is 0.282 actually. Okay, let me now do this calculation. So, this into 2 into 1.542, which gives us, doing the division, 2.73 Armstrong. Now, I have told you that this corresponds to H equal to 1, K equal to 1, L equal to 0. That is the next set of Miller indices, and D is equal to A by, in this case it is going to be A by square root of 2, or we can use this to calculate A. A is square root of 2 into 2.73 Armstrong, which comes out to be 3.87. So, we see that we can use the next line, the line at the next value, higher value of theta, to also determine the unit cell, and we get exactly the same answer as we had done earlier. Okay, so you can check. I will leave it for you as an exercise to go through this. So, what you can do is you can check that all of these angles, if you find the lattice constant, by lattice constant we mean the spacing between these unit cells, and if you use all of these different lines that you have over here, I have given you 3 of the angles corresponding to 3 of them, and if you determine the atomic interatomic spacing using this data, each of them you can interpret the first one as corresponding to HKL equal to 100, the second one as corresponding to 110, the third one as corresponding to 111, successively smaller, larger and larger interplanar spacing. So, as you increase the values of H, K and L, the spacing between these is going to get smaller and smaller, and as the spacing D gets smaller, the angle theta over here, as the spacing D gets smaller, the angle theta has to increase, and we can interpret these successive lines as corresponding to larger and larger values of H, K and L, and we can use this to get the interatomic, the lattice constant or the periodicity of this lattice. So, what I have tried to show you here is some basic idea of X-ray diffraction. X-ray diffraction is a very useful tool to determining the structure of materials, and here I have shown you how you can use it to determine the lattice spacing of a cubic crystal. We have considered the simplest possible situation where you have a cubic crystal. There are more complicated situations where you have different kinds of crystal structures. You could have tetrahedral crystals and various kinds, rhombohedral crystals, different kinds of crystals, and the subject of X-ray diffraction is quite an involved subject. I have tried to give you only a glimpse of how the thing X-ray diffraction works. It is essentially just an extension of the basic idea where each atom acts like a source and you have a periodic arrangement of these sources, but it is the whole thing gets gets quite complicated as you go into more and more complicated atomic structures, more and more complicated crystals, but it is a very useful tool, and it has got wide applications in physics, in metallurgy, where you are interested in finding the structure of solids. So, if you have a crystalline solid and you want to find how the atoms are arranged inside, then you can use this tool of X-ray diffraction to determine this. The location of the diffraction, the intensity maximas in the X-ray diffraction pattern tells you about the structure of the atoms inside, how the atoms are distributed inside. Finally, I should also mention that this tool of X-ray diffraction has wide applications also in determining the structure of biological materials, for example, of proteins, of the DNA. The structure of DNA was actually discovered by using this tool of X-ray diffraction. The structure of proteins are also determined using X-ray diffraction. The problem there is you have to first crystallize the protein, and once you have a crystal, you then bombard it with, you send incident X-ray and you get a diffraction pattern. The diffraction pattern there is quite complicated, and interpreting it is a very difficult exercise, and that is where the challenge comes in. Interpreting the challenge is actually in two places, in crystallizing the substance and in interpreting the diffraction pattern. So, in this lecture I have tried to tell you about a three-dimensional situation where you have diffraction, and tried to show you an application of X-ray diffraction. I leave the problem to you to actually work out the lattice constant from this data. So, the data which I have given you, let me just remind you again, we have readings of 2 theta from the X-ray diffractometer, and I have told you that we can interpret the smallest value of 2 theta as arising from the Miller indices, the planes with the Miller indices 1 0 0, and the next maxima as arising from 1 1 0, and the one after that as arising from 1 1 1, and so forth. And I leave it to you to check that if you calculate the lattice constant A using 3 of these, you will get the same value of A. And the main purpose of this exercise is to give you an idea of how you can use X-ray diffraction to determine the structure of solids, of crystalline solids. Here you can determine the lattice constant. In more complicated solids where you have non-cubic structures, you can also determine the kind of arrangement you have and various other things. So, let me stop here and continue in tomorrow's lecture.